All right, which web work we got going on?
It's number 6.
What's it say?
And it's f(x) equals the one, sine of a over x, sine ax over x. If x is less than 0, 5 if x is equal to 0. And then x plus b if x is greater than 0.
We want to find the values of a and b that make this continuous for all functions x. And values of a and b, so f is continuous for all values of x. Function's continuous at a point if it does 3 things. Continuous at x is equal to a if f of a exists. If the limit as x goes to a of f of x exists, and if they're both the same number, then a function's continuous on an interval if it's continuous at every point. So when we look at these 3 pieces, the only thing that we should be concerned about is dividing by 0. Sine is always continuous. That's just a single point, and that's a linear function. So we're only worried about 0, which happens to be where this thing changes shape. So what we need is we need those 3 things. F of 0 needs to exist. We need to be able to have a limit as x goes to 0. And we need those 2 things to be the same. We can make this continuous that x is equal to 0 with the right choice for a and b, and we know it's going to be continuous for all x. So f of 0 is defined. F of 0 is 5. For the limit, we've got pieces that are on the left-hand side of 0 and on the right-hand side of 0. So we've got to compute this limit by doing the left and right limits. So let's go over here and look at the limit as x goes to 0 from the left-hand side. From the left-hand side, we're looking at this piece. The sine of a times x divided by x. And that's one of our special limits. What's the sine of a times x divided by x? It's going to be, it's going to be a, right? When there's a number here and a number here, the limit as x goes to 0 is a over that number. So I get a over 1, which is a. Now we're going to take the limit as x goes to 0 from the right. And when on the right-hand side of 0, we use x plus b. And since that's a linear function, we can take this limit by putting 0 in for x. You put 0 in for x, we get b. So we need a to equal b in order for this limit to exist. And if a and b are equal and they have to be the value of the function, take a wild guess what a and b have to be. Both a and b must be 5. And there's our answer. Is that okay with y'all? What else you need? Yes, ma'am.
Can you go over 14?
Sure. And you tell me what 14 says?
part A is the limit as x goes to 0 with a negative sign. It's e to the power of 1 over x.
Okay,
And then part B is the limit that goes to 0 with a positive sign. It's the natural log of x.
those are both of them.
Yes.
So this kind of jumped the gun. It kind of goes into section 4 where you have to know a little bit about the behavior of our exponential functions and perhaps even their graphs. So let me remind you what the graphs of these things look like. The graph of y is equal to e to the x is a growth curve. And the log curve is the inverse of that. So if I flip that about the line y is equal to x, it does something like this. Where this point here is 0, 1. And this point here is 1, 0. So we can do part B first. If you're on that graph of that log function and x is heading towards 0 from the right, describe for me what the graph is doing. Second graph, x is heading to 0 from the right, follow the graph. It's going to keep going down and down and down, so it's going to go to minus infinity. So if I just write that over here, as x goes to infinity, the natural log of x goes to infinity. But as x goes to 0 from the right, the natural log of x goes to minus infinity. Here the graph keeps growing. Here the graph gets real small. Big, small negative number, big negative number. How about that? Now don't look at this exponent, but this picture says that as you ride the x's out to positive infinity, the graph also goes to positive infinity. But if you ride the graph out to minus infinity, the graph goes to 0. So we're looking right here. We're looking at 1 over x as x goes to 0 from the left. What happens to that? So for this one, first, what happens to 1 over x as x becomes small, but to the left of 0? For instance, a negative 1 over 100, a negative 1 over 200. What happens if I put those numbers in for x? Negative 1 over 1,000. And negative, right? You're going to get a big old negative number. Right? So if I put numbers in to the left of 0, they're negative and they're small. Flip over a negative small number and you get a negative big number. So this exponent's going to minus infinity. And what we said over here is that that goes to 0. Okay. So the first one goes to 0 because e goes to minus, it looks like e to the minus infinity. The second one looks like the natural log of a small positive number, and those all go to big negative numbers. So if you know what the graph looks like, this just tells you where to look. You need another one? Oh. That's what I said right there. Yes,
Yeah.
I'm ready.
Okay. Number 10. 2 to the power of log base 4, log base 2, print 4. minus log base 2 power 3.
So all of this stuff is up in the exponent. So let me refresh your memories about logarithms. This is where we ended class last time. So here is everything you know about logarithms. First, there's the definition. A logarithm finds an exponent. A logarithm base b of a value v is an exponent u if and only if b raised to that u power is v. And all of our logarithms are inverses of exponential functions. That's what that says. If you swap places with u and v and solve for v, that's what you get. I'm sorry, solve for u. And so what that says is that the logarithm base b of b is 1. In terms of our other logarithms, I can say that in terms of a log base 10 of 10 is 1. And in terms of a natural logarithm, the natural log of e is 1. We also have the picture that says any log of 1 is 0. So the log base b of 1 is always 0. So in terms of a log base 10 and a natural log, we have that. Then we ended class with the exponential properties of logs. Logs were exponents, so that when you multiply like bases, you add exponents. When you raise a power to a power, you multiply exponents. And when you divide like bases, you subtract exponents. So in terms of logarithms, those three things look like this. That a logarithm, base b, of two things multiplied together. Let me use m and n. Don't get the b's all mixed up. Multiply like bases means you add exponents. Multiply like bases and you add exponents. Raise a power to a power, then it looks like this. Logarithm base b of m to a power looks like the product of the two logarithms. B times the log base b of m. And then when you divide, you subtract exponents. So if I have my article of the logarithm as a fraction, you subtract exponents. So we're going to write that as log base b of m minus the log base b of n. And so we are going to use this one and this one to figure out what this value is. This says the inverse relationship one way. The other way looks like this. Logarithms and exponential functions are inverses of one another. So if you have base b here and the logarithm base b here of anything, it gives you back the anything. And so for base 10, it looks like this. And for a natural logarithm, it looks like this. That's the inverse relationship, and so is that. In fact, I can generalize this if I put a power up here. Let's just put the number a up here, and the number a there, and the number a there. So these all become a's, whatever the exponent is. that over here a little bit. Okay, so I gotta move this a bit over so we can all see it. Number 10 looks like this. 2 to the logarithm base 2 of 4 minus the logarithm base 2 of 3. So I'm only looking at the exponent, and in the exponent, I see the difference in 2 logarithms. And so what this property says is, if I've got the difference in 2 logarithms that are the same base, I can put them together as a single logarithm just by dividing the articles of the logarithm by each other. So I can combine, black isn't working right for me. Back to blue. I can combine those 2 logarithms as a single logarithm, where I take this 4 and divide it by that 3. That's this property right here. Then I have the inverse relationship from up here. If the exponent is a logarithm that is the same base as the exponential function, those 2 operations undo each other, and we get the input value back. So the last step here is to recognize that, and we should just get 4/3 out of this. Okay? Yeah, another one? Okay, I want to get more practice using these, so let's do some of my examples. Let's see where I was. I think we wrote the basic properties of logarithms, and we were going to solve some log equations. But before we do that, let's do just a small example here using these log properties. And let's take this logarithm, logarithm base 3 of about 27 x to the 4th divided by y to the 6th. Take that single logarithm and let's write it in terms of simple logarithms. Later on in chapter 3 and chapter 4, we're going to want to do something with these logarithms. And when we have the log of a big old mess, it makes that task difficult. But if we were able to spread it out in terms of easier looking logarithms, then our task becomes relatively simple. So that's what I'm asking you to do here. Spread this out in terms of simpler logarithms. So the first thing I want you to notice is that the thing in the parentheses there is a fraction. So we've got to do our order of operations kind of thing. So I'm going to take that fraction and I'm going to divide it up and make that 2 logarithms. The log of the top part minus the log of the bottom part. That's this property. Take the log of the top, subtract the log of the bottom. So there's nothing I could do to this. That's just an expression in terms of the variable y. But here I've got 2 things multiplied. Oops, that should be a y to the 6th. Never mind, I take that back. There will be something we can do with that. I'm gonna do that last. I'm gonna work here next. I've got the log of a product, and the first property that I've written over there says that the log of a product can be written as the sum of two different logarithms. The log of the first factor plus the log of the second factor. So I'm going to write this as the log base 3 of 27 plus the log base 3 of x to the fourth. So I get the log base 3 of 27 plus the log base 3 of x to the fourth minus the log base 3 of y to the sixth. So the other property that we haven't used yet, we'll take care of the exponents. The power on the x is going to come down in front. The power on the y is going to come down in front. And another thing that we haven't used yet is the definition. The log base 3 of 27 is a number that we know and love. It's a power that goes on the base to give us 27. 3 to what power is 27? 3. So this is just 3. Here the power comes in front, and this power comes in front. So I'm going to have plus 4 times the log base 3 of x minus 6 times the log base 3 of y. And you can put those in parentheses if you want, or you can just leave them just like that. So that's one way we're going to use these log properties. The other way is if you have several logarithms, we can mush them together and make one logarithm. And that's usually one of our strategies when we have an equation in which terms in the equation are logarithms that are added or subtracted from one another. Did I do something wrong? Is there a 3? Oh yeah, that's a log base 3. Thank you. I'm a proofreader. I need you when I make tests. I always make mistakes on my test, every single time. Okay, so let's look at our log equations. And our strategy in our log equations is to either get the single logarithm on one side and a number on the other, or logarithms are one-to-one functions. If I get a log on one side and a log on the other, then by the one-to-one property, the articles of the logarithms are the same. So one more thing I want to write down here about logs is that if I have a logarithm base b of one number equal to a logarithm base b of another number, then the only way that can happen is if these two numbers are the same. They're one-to-one functions. So in solving log equations, equations that have logarithms as some of the terms, we either want to get one log equal to a number or one log equal to another log. If we can do that using these properties, then we can just go either to here or to there to solve the equation. So I'm back on my worksheet. And I'm going to write it right here. And the instructions are to solve each of the following log equations. The first one says logarithm base 5 of x minus 2 is equal to 2. So we already have this statement. We've got this statement on the left. We've got it in its log form. I think it'll be easy to solve if we change it to the equivalent exponential form. So the exponential form says that I take the b, I raise it to the u power, and set it equal to v. So here I take the 5, set it equal to the second power, raise it to the second power, set it equal to x minus 2. Base raised to the right-hand side is equal to the article of the logarithm. So 5 to the second is x minus 2. And now that's just a linear equation. We have 25 on one side, x minus 2 on the other. So x has to be 27. And then you can quickly check your answer. If x is 27, then inside here I've got 25. So this says 5 to the second is 25. That works where I come from. The other one set up for you as well. We've got a single logarithm equal to a number. So in number 2, we have the log base x of 64 is equal to 2. Single logarithm is equal to a number. Just convert it to its exponential form. So it's the base of the logarithm raised to the right-hand side is equal to the article of the logarithm. This gives me the equation x raised to the second power is equal to 64. You got anything you can raise to the second power to get 64? And we discard the -8 because the base of logarithm by our definition has to be a positive number. Has to be a positive number other than 1. 8 is it. All right. Third example has 2 logarithms added together and equal to a number. I have a log base 6 of x, a log base 6 of x plus 5 added to that is equal to 2. So I want to make this problem as easy as the last one by getting a single logarithm over here. I can't change it to exponential form until that's a single logarithm. So find you a property that we can use to write that as one log. I got a plus sign here. I got a plus sign here. So I put them together by multiplying the 2 articles together. One logarithm, but I take the 2 articles of the logarithms and multiply them together. So I keep that as a log base 6. But now I'm going to take my x and multiply it with the x plus 5. So I can write that as x squared plus 5x in there. Now we do what we did the second ago. Base raised to the right-hand side is equal to the article of the logarithm. 6 squared is x squared plus 5x. Since that's a second degree equation, I'm going to get a 0 on one side and try to factor. So I'm going to take that 6 squared, write it as 36, and then subtract it from both sides. And I get 0 is x squared plus 5x minus 36. So now you're looking for factors of 36, opposite in sign, that add to a positive 5. Got any numbers that multiply to 36 but add to 5? 9 and which one? -4. I like that. X plus 9, x minus 4. times 9 is 36. 9 minus 4 is 5. Now you set each factor equal to 0, and you get two solutions. You get x is equal to -9, and you get x is equal to +4. But now remember the domains of the logarithms. We can never take the logarithm of 0 or any negative numbers. The order of the logarithm has to be strictly positive. So we ditch this one. We can't have the log of a negative number. So 4 is our keeper. Make a quick check. 4 squared is 16. 16 plus 20 is 36. Log base 6 of 36 is the power of 2 on 6. All right, I'm gonna erase this stuff over here. So this has to be now in your memory. I need some more room to write. So my fourth one. Fourth one. I'll do red. Red shows up better. We have logarithms base 2 all over the place. We've got 2 of them on the left-hand side. Looks like a logarithm base 2 of x plus log base 2 of x minus 4 is equal to the log base 2 of x plus 6. So the difference is I don't have a single number over here. So my strategy this time is to get one logarithm on one side of the equal sign and a logarithm on the other side and use the one-to-one property. So can you see that? I don't think you can see that. A little bit. There it is. It's the log base 2 of x plus the log base 2 of x minus 4 is equal to the log base 2 of x plus 6. So those two logarithms on the left-hand side are separated by a plus sign. And we've just seen that if they're separated by a plus sign, you make one logarithm by multiplying. We'll put these two together and write that as the log base 2. Multiply those, and we'll go ahead and write that step in as x squared minus 4x. Now I've got a log base 2 equal to a log base 2, and the only way that can happen is if this is equal to that. So we just said x squared minus 4x equal to x plus 6. Yeah, we got a second degree equation. Let's get 0 on one side and then try to factor. So I'm going to move those guys to this side, and we'll write that as x squared minus 5x minus 6 is equal to 0. Look for factors of 6, opposite in sign, that add a -5. The key is these factors have to be opposite in sign. What are they going to be? 6 and 1. I want a minus in the middle, so let's make the 6 minus and the 1 plus. So -6 times +1 gives me a -6 out here. -6 plus +1 gives me the -5 there. And as before, set each factor equal to 0, and you get x is 6, x is -1, but x is -1 is a problem child, throw it away. You can't have the log of a negative number. The 6 makes everything positive, so that's the one we keep. Okay. Oh my gosh, there's more on back. All right, we got a number 5. I can put that right here. With the short problem, I have 2 log x is equal to the log of 49. If that 2 weren't here, then I have what I had before, a single logarithm equal to a single logarithm, both of the same base. But the 2 is there, so we've got to take care of it first. Where does that 2 go?
Exponent.
As an exponent. I can either divide it out or I can put it as an exponent. The exponent works better for us in this case. So that's a property of logarithms. Coefficients become powers. So now I have the log of x squared is the log of 49. One log is equal to another log. They're both logarithms base 10. That allows me to get rid of the logarithms and just work with the x squared is 49. I know this equation has 2 solutions, but I only want the positive one. So our answer is x is 7. Okay. All right, the next one. This is kind of an interesting one, I say, because I wrote the problem. Number 6 says is now an exponential equation. Number 6 has 10, and in its exponent is the log of x. And on the right-hand side, we have 4 is equal to the log base 2 of 8. Any thoughts rolling through your head here? What'd you think of when I wrote down 10 raised to the log of x? That's just x, because those 2 are inverses of one another. That's the inverse relationship. 10 with a log base 10 in its power just gives you the original input. So over here, I just get x. Do you know the value of the log base 2 of 8?
3.
Because 2 to the 3 gives you 8. Log base 2 of 8 is a power on 2 that gives you 8. So log base 2 of 8 is just 3. And then we can go ahead and cube 4. 4 times 4 is 16 times 4 more gives us 64. Okay, then this power, this property that a logarithm takes a coefficient, makes it a power, is often used the other way as well. The logarithm of something to a power can be written as the coefficient times that logarithm. And that means if we're trying to solve some exponential equations and we want to pull the power down, we can use a logarithm. And I'll show you how in the next 2 examples. It says use a logarithm to solve these exponential equations. The first one, we have e raised to the 2x, then the one's down here, it's not up there with the power, and then that's equal to 15. E to the 2x minus 1 is 15. So first we can get the like terms together. I add that 1 to both sides and write that as e to the 2x is 16. Just like we like the logarithms by themselves, we want the exponential functions by themselves. Add 1 to both sides. Then I know logarithms have the property that they pull down powers. I also know that a logarithm base e of anything gives us that anything. So I'm going to take this equation and do the same thing to both sides. And the thing that I'm going to do is I'm going to take the natural log of both sides. Take the natural log of e to the 2x. I'm going to take the natural log of 16. Like I said, these guys are inverses of one another. So the natural log of e to the 2x is just 2x. The natural log of 16 is a power that goes on e to give you 16. And since e is an irrational number, we're not going to be able to come up with that power. So let's just leave that as the natural log of 16. It's some irrational number. We're done once we divide by 2. And that 2 is into the log of 16. It's not something that I can move into the 16. Okay? If you wanted, though, I could do this. Agree that those are the same? And now it's a coefficient, and I can put as a power on the 16. Does anybody know what the 1/2 power of 16 is? It's 4, because a half power is a square root. So I can write that as the natural log of 4. The answer is the natural log of 4. Okay. Second one. I got 6x is equal to 1,000. Let's see, 6 to the first power is 6, 6 to the second power is 64, 6 to the third power, let's see, what's 64 times 6? 4 times 6, 4, 18. That's, I don't know, what is 6 cubed? $384. So 6 to the fourth is 384 times 6, and that's already bigger than 1,000. So the answer to this equation is some number between 3 and 4, probably a bit closer to 4. Again, it's going to be an irrational number. So if I want to find that irrational number, my job is to get that exponent down. So I'm going to get it down by taking the logarithm of both sides. But this time, instead of using a natural logarithm, I'm going to use a logarithm base 10. Because I know the logarithm base 10 of 1,000. I'll take the log of 6 to the x and set that equal to the log of 1,000. What is the log of 1,000? It is 3. 10 cubed is 1,000. Over here, I just have x times the log of 6. The log of 6 we don't know. That's just like in the last example. That's an irrational number. My job was solving for x, so we divide both sides by that irrational number, and we get x is equal to 3 divided by the log of 6. And then if you had a calculator, you can punch that in and get an approximation, and I bet you $1 it's a number between 3 and 4. Did any of those examples make you think of some questions you wanted to ask? No? So I really think outside of doing limits, we haven't really touched on any calculus yet. We're going to start some calculus in chapter 3. Limits were a very, very minor part. We're going to learn better ways of taking limits. So let's look at one of the main ideas of calculus. Remember, in calculus, we were interested in how quantities change with relation to one another. You've got a domain paired with a range, and if you make changes here, how does that force a change there? Where they're not incremental steps, but they're in continuous steps. Just like with limits, x is approaching a number. What is the expression approach? Measuring how things change with respect to each other. So again, chapter 3, we're going to start talking about instantaneous rates of change. First, the geometric aspect. So I'm going to draw you the graph of a continuous function here. Start way on the left. That black marker. See what that one on the windowsill looks like. Ain't bad. Then look at something called an introduction to the derivative. Draw my function to look like this. That's the function y is equal to f of x. Let's just put the x and y plane on here somewhere. Y-axis coming through here. And the x-axis down here. Let's consider a point P, about right here. And x is equal to a, so that y value corresponding to point P is whatever the equation is. I'd have to evaluate it, and x is a. So point P corresponds to the ordered pair A, f of A. What we want to do with this is we want to find the slope of the function at x is equal to a. Well, we know what it means to be the slope of a line. The line of the slope is that number in front of the x. Y is equal to mx plus b. And no matter which point you're on a line, the slope is the same. It's whatever the change in y is per change in x. But where you want to graph depends on where you are on the graph. For instance, if my finger were here, my slope looks like it should lean downward, should be some sort of negative number. But where my point is here, my graph is leaning upward, so I should have some sort of positive slope. If I'm up here at the top, then it looks like I'm not leaning at all, so my slope should be 0. So where I am depends on what the value of the slope is. So I think, well, I'm going to find the slope by using my formula, change in y over the change in x. The only problem with that is I only have a single point. So I'm going to grab a nearby point and connect it with a line segment and find the slope of that line segment. So even though it looks like it's far away, I'm going to use this point right here. Q, Q. So pick a point near, pick a point, come on markers. point on the graph near point P, say at point Q. And I'm going to find the slope of the line that connects point P with Q. We're going to find the slope of the line through points P and Q. So let's figure out where point Q is. Let's say it's close to point P. So in other words, this X coordinate is close to that one. Let's say that I've gone H units this way. So for instance, if A represents 2, this could be a number like 2.1. So it's 0.1 away from 2. And if that's the value of X, and I want to get the Y value, I take my formula for the equation, which is f of X. I plug that in for X and I crank out the Y value. So if this is 2 and that's 2.1, I find f of 2.1. So I'm going to go over here and label that Y value as f at A plus H. And now the slope of the line through points P and Q will be the change in Y over the change in X. This Y minus that Y divided by that X minus that X. Okay, so I'm going to write that. I'm going to write the slope of the line through points P and Q. Let's write it that way with a little line on it. Is equal to the change in Y over the change in X. Are you familiar with the little triangle? That's the lowercase letter delta. And in math, it means change in. Y2 minus Y1 divided by X2 minus X1. In our picture, our Y2 is going to be f at A plus H. And my Y1 is f of A. And then downstairs, I take the difference in the X's, A plus H minus A. There's not much I can do with the numerator. So let's just leave that as it is, f of A plus H minus f at A, all divided by, well, these are 3 different numbers, but the A's are the same, so A minus A is going to leave me with the H. And my thought is that that's roughly going to be how steep the graph is at point P. Except any of you that has eyeballs in your head can see that this slope doesn't look anywhere like that slope. My interpretation of the slope of f at P would be the slope of this line. The line that touches the graph at point P, but only at point P, in the neighborhood of point P. That such line is called a tangent line. The idea is that the slope of the tangent line to the graph of y is equal to f of x at point P is roughly equal to the slope of the secant line that we just found. Kinda. My problem is that I probably should have used a point a little bit closer. I drew that one so far away. What if I picked one, say, about right here? Let's call this point, call that one point Q1 and call this one point Q2. The secant line that connects P to Q2 is closer in slope to the red line. So all I gotta do is take this number to be a smaller number, pick h to be smaller. Move it back here a bit. So make that a plus h. But then there's still a bit of a difference, can't really see because of my markers. But what if I took it even closer? Slide that point closer, grab point Q3, make that closer, and say that this is the point A plus H. And keep doing that and keep doing that. Keep sliding this point closer and closer so that the difference between point P and whatever iteration on point Q is, to the naked eye, looks like there isn't any distance there. Like if you stood right here and put your eyeball right on that point, you couldn't see the difference between point P and Q. And I don't have to do that manually. I can do that with calculus. When I'm sliding that point closer to this point, I'm making this number h smaller and smaller and smaller. Okay, so we're going to slide point Q toward point P by making h smaller and smaller, until eventually there's no distance between point P and Q. I'm still finding a distance between distinct points that are not really distinct, just by taking this number to get smaller and smaller. And so we have this, that the slope of the tangent line is equal to the slope of the secant line, f at a plus h minus f at a divided by h, but we're making the distance between a plus h and a to be really, really small. In calculus, we write it like this. We're going to do a limit as h goes to 0. Pick any 2 points on the graph. Well, make one of them point plus h. Then find the slope using y2 minus y1 divided by x2 minus x1, and squish the points together with a limit, and you have the slope of the tangent line to the graph at f, which is going to be considered the slope of f at that particular point. Now I'm going to show you that that calculation is a calculation that we can do, but in a different interpretation. So here's another approach where this calculation shows up. Before I do the calculation, let's take a number line. Given a number line, and imagine that an object moves along this number line. In such a way with its position at time t, its position at time t given by s at time t. So maybe this is the origin. And maybe in my first time measurement, I noticed that particle is right here. So that this is s of, say, t1. It keeps moving to the right, maybe. So maybe later on it's here, s of t2. Maybe later on it's further out here. Whenever I want to look at it, I can find it at a different point on the number line. But just consider those two positions. A time interval from time 1 to time 2. So on the time interval t1 to t2, the position change from S at T1 to S at T2. Now, I want to know how fast this little particle is moving. Well, maybe it changes speed. Maybe it's going slow and speeds up and maybe goes slow again. So its rate of change varies. But on a time interval, I can find an approximation or at least an average velocity, right? If I'm driving from here, from Lubbock to Dallas, that's roughly 360 miles. And if it took me 6 hours to do it, what's my average velocity? I go 360 miles in 6 hours. I'm doing 60 miles an hour. But I'm not, because you know there's that little piece in there by Dickens where you can just really lay it on hard. And then you get to Seymour. There's a Dairy Queen. I got to stop and get me a dip cone. So I'm not moving it all there, and around Dickens, I'm really hauling it. But on the average, I did 60 miles per hour. So it takes into consideration going above 60 and below 60. Well, if I want to find an average velocity of this particle, I got to do the same thing. I can find out a distance traveled and divide it by an elapsed time. So the average velocity of this particle on that time interval is going to be the distance traveled, so the change in position, S at T2 minus S at T1 divided by T2 minus T1. Change in position divided by change in time. So I can write it like this: delta S over delta T, just like I did over here. Now, if I want to know how fast this particle is moving right at that instant, and I don't have a little radar gun, or I don't have a particle that can look at the speedometer and see how fast it's moving at that instant, then all I've got to do is mimic what I did there. So I can say that if I want to find the velocity at the point where at T1, just pick T2 to be a smidge further than T1, say T1 plus H seconds later. Find this distance between T1 plus H and T1 and divide it by the elapsed time. So find the velocity at time T1. Consider the interval from T1 to T1 plus H, and do the same thing. Compute the average velocity by computing the change in position over the change in time. The change in position is going to be S at the T1 plus H. That's its new position, right? I'm going to go to here. Subtract off the position at that time, and then divide by the difference or the elapsed time. The T1s subtract each other out, just like the variable X did over here. Now we make an average rate of change into an instantaneous rate of change by letting the elapsed time go to 0. As this elapsed time H goes to 0, I'm finding average velocity over shorter and shorter intervals. So if we take H to 0, we can make this an instantaneous velocity. And so I write it like this. I write a limit as h goes to 0 of s of t1 plus h minus s at t1, all divided by h. And you see the exact same calculation that we did just a second ago. This thing here, we called the difference quotient when we were in chapter 1. We were finding f of a plus h minus f of a divided by h. Now we're going to call it an instantaneous rate of change simply by computing that difference quotient as a function of h, then taking h to be 0. And it can be interpreted as an instantaneous velocity or a slope of the tangent line. And this can be called the derivative of whatever function we have in terms of its graph or position. Okay, so it's the same calculation. It'll be called the derivative of f at that particular point. So both of these involve changing a position, a motion. What happens to the slope if I move the secant line into a tangent line? What happens to an average velocity as we move the interval to 0? Well, it becomes an instantaneous velocity. Its rate of change at a point is what makes it calculus. So we define the derivative of some function y is equal to f of x at the point x is equal to a as being this limit of the difference quotient as h goes to 0 of f at a plus h minus f at a, all divided by h. We're going to denote the difference quotient as change in y over change in x. And so if I do that up here, I'm going to write this as the limit as h goes to 0 of change in y over change in x. So we do that, and when we compute the limit of this reduced expression, then these Greek letter deltas become our d's, dy over dx. So when you see deltas, that's an average. When you see the d over the dx, that's an instantaneous. And you read this as the derivative of y with respect to x. There's the y. This notation is handy because it shows you the relationship between the average rate of change and an instantaneous rate of change. But since we're in calculus 1, in which we only have one independent variable, we can also denote the derivative using a prime notation. My y is a function of x, and so we're going to denote its derivative as f prime of x. Get used to both notations. You'll see some lend themselves better to with what we're talking about. I like the function notation when I'm interested in the derivative at several points. F prime of x, then I can find f prime of 1, f prime of 7, f prime of negative pi, just by doing a substitution. This notation is going to be handy when we talk about derivatives with respect to time. Or if you have a function of several variables, then we can tell you what variable that you're taking the derivative with respect to. So when you're in Cal 3 later on. I might have time to do one of these. No? No? Are you saying that this is not the kind of class that you want to hang into? God. Let me make a quick note on who said that no. I'll do a small one. Y is equal to x squared.
2x.
So you've had this calculus stuff before. Anybody in here never, ever, ever had calculus? Good, then I'm gonna take my time. Well, kind of, because I only have like 5 minutes left. Draw me the graph of y is equal to x squared. It's a parabola that opens upward. It's steeper, say, at x is 4 than it is at x is 1. Eraser, where'd you go? Okay, so here's the pen. Consider y or f of x, whichever way you want to do it, is x squared. It goes through 0, 0, 1, 1, 2, 4. And it does the same thing back here. But the slope of the tangent line here is not as steep as the slope of the tangent line is there. This should be a bigger positive number than it is here. Okay, so my task here in this example is I'm going to find the slope of the tangent line at x is equal to 1. Now at x is equal to 1, so is y. That's the ordered pair 1, 1. I'm going to move over here to the point 1 plus h. And I'm going to go up there and plot that point right here. And we're going to find the y value, and then I'm going to slide that h in. Okay, so we pick a nearby point. Where x is 1 plus h. At x is 1, y is 1. At x is 1 plus h, y is 1 plus h all squared. I just plugged that in there. Right? Took the 1 plus h, put it into that equation. Then I'm going to compute the change in y over the change in x. By taking the 1 plus h squared minus the 1 and divide it by 1 plus h minus 1. And the ones add out on the bottom, and it leaves me 1 plus h squared minus 1 over h. Now to make that the slope at that particular point, we simply take the limit as h goes to 0. So the slope of the tangent line at x is 1 is found by taking the limit as h goes to 0. But if you replace h with 0 right here, you get 0 over 0. So we do more. We do the squaring. So 1 plus h squared is 1 plus 2h plus h squared. Then I got the minus 1 here, and then the h there. Right? 3 terms from squaring that, then the minus 1, and then the h. But the one in the front subtracts with the one in the back. I have 3 terms left now, and they all have an h in them. So I factor out an h and cancel it. Factor out an h, and the top can be written as h times 2 plus h. Cancel it. And now I can take the limit as h goes to 0, and I get 2. That 2 is going to be called the derivative of this function when x is equal to 1. Then if I want to find what the slope is when x is 4, I just do the same thing. I start at x is 4, and I find a point nearby at 4 plus h, and I do this calculation again. And I'll do that next time. So for each point, we can move it over by h units, find the change in y over the change in x, then take the limit as h goes to 0 to give us the slope of the tangent line to the graph. It's all good? Questions at home, anybody? Okay, I'm shutting the camera off here so I can move the board out of the way. If you have a question, please ask it.